what we're doing is, so you're having trouble writing again because the board, of course, is always worse than before. So use the first derivative to find the relative extrema, maximums or minimums. So remember, just reminding us that the first derivative was negative 6x squared. The original was negative 3x cubed. And as Grace said, we're graphing the derivative again. So we're graphing the derivative, which will be like this. It'll just be because we know quadratics pretty well. We know it's got a y-intercept of 0. And we already know by solving, setting it equal to 0, we already know that it's kind of like there. So notice that if you were to make this, the gradient is negative here because it's down the bottom, and it's also negative here. So because the gradient is always under the x-axis, which means it's in the negative area. Because our y thing, this looks bad because it's over here, so I'll draw it over here instead. So our y, g dash of x. So label the y-axis g dash of x because it's a derivative, because this topic's all about graphs of derivatives. G dash of x. So the original's cubic, so the derivatives, of course, are quadratic. And because the whole quadratic's under the x-axis, it means that it's one of these ones where the original one would have dropped down like that. Because it's decreasing, then hits 0 at the point of inflection, then decreasing again. So don't feel like you need to draw that, because we do that later anyway. So either side, the gradient is of the turning point. What's it called? Of the extrema. It's a point of inflection. So use the first derivative to find the relative extrema. By that we mean maximums or minimums. Does the original function will kind of look like this. Are there any maximums or minimums?
No, just
no.
Yeah,
exactly. So our answer is there is no maximum or minimum, as it's just a point of inflection. There's no.
There are then.
Yeah, that's better. There is no max or min. Using shocking grammar. As you could say it's a point of inflection. We call POI.
Wait, so what would the original graph look like?
Because it's a negative gradient either side, the original would have been going down like that. Whereas if the graph was all above the x-axis, the original would have been more like that.
Can we draw? I'm going to draw the original.
Yeah, that's a good idea. Yeah, that helps kind of
Does it matter
understand what's going on. Sorry, I'll put them back. What are you saying?
No, never mind.
Yeah.
So the point of inflection would be at the origin?
Yeah, just here, yeah. So the point of inflection, yeah, would coincide with this little point of here, yeah.
How do you know that it's decreasing on both sides?
Because see the graph of the derivative is all in the negative y area. So the derivative was constantly negative here and negative here. Whereas if it was up above, then the derivative is positive all the time, except for the point of inflection. So I said this is pretty confusing stuff when you first exposed to it. There is no max or min, it's a point of inflection.
OG funk.
It's a POI. You could say as the derivative is negative, as the derivative doesn't change sign after a stationary point. So a point of inflection, a maximum and a minimum, they're all examples of stationary points. So you could say the derivative, or the value of the derivative does not change sign.
Does not change
sign after the stationary point. That's another extra thing you can put in as a reasoning. Because maximums, minimums, points of inflections, they're all types of stationary points, they call them. So the reason why it's a POI as opposed to a maximum or a minimum is the derivative doesn't change sign. It's still in the negative area because it's below. See, this is the derivative.
You said that's the reason why it's a POI?
Yeah, because the derivative doesn't change sign. Because if it was a maximum or a minimum,
it would change.
It would change sign, yeah. You'll see the second example is one where it does change sign. Because the derivative graph crosses over. So part of it's positive, part of it's negative. So there's no maximum or minimum. It's a point of inflection. Another reasoning is the derivative doesn't change sign. It's still negative. It's in the negative y area after the stationary sign. Good stuff. So we're just doing the top of page 25, Davina. Okay, let's move down a bit. And I'll cross this one off. So that was that one. What was the value of the derivative for the second example?
Divided to the regular.
Yeah.
12x squared is 24x minus 36.
So that's only one.
Yeah, I know. That's why it's a pain. So it's split into three different parts again. So the second example was f dash x, which is the derivative was 12x squared plus 24x minus 36, like Grace just said. Just reminding ourselves. So we already know where the two critical points are, where the two stationary points are. Where were they from the previous page? One at x equals something and one at x equals another thing. Yeah, x equals 1, x equals negative 3. We already know where.
That's irritating.
Sometimes I call them critical, sometimes I call them, oh, that's annoying. Critical points, that's meant to say. X equals negative 3. That's bad. Okay, I'm probably going to have to practice for you. That's messed up.
Critical.
Yeah, so what this says, by the way, because the pen's messed up again, we already know there are critical points at x equals negative 3 and x equals 1. That was from the previous page. So we already know by the type, because we already know that the original one, it's kind of one of those roller coaster ones, where it's either going down or up like that, or up and down like that. And remember, we worked out that it was one where, oh sorry, oh, you're all writing, so I won't look on the previous page, I'll look on my one here instead. Oh, it's positive. From the previous page, we could tell from the gradient it was positive, then negative, then positive. So it's a roller coaster going up and down like that. So therefore, we worked out from the previous page that the original function's more like one of these ones because it was increasing to begin with, then decreasing, and then increasing again. That's meant to be just a regular roller coaster. There's not meant to be a... That's awful. So, just pointing out that the original one's kind of in this style. And continuing on that way, continuing going down that way. So, therefore, would you say that the one at x equals negative 3...
That's the original function, right?
Yeah, this one's the original. Yeah, that's a good point. Let's make a note of that. This is the original function. This is something we worked out on the previous page. So it's kind of in this shape. The original function.
You can write OG.
Yeah, the OG. The original function. So therefore, x equals negative 3, is that a maximum or a minimum?
Wait, x equals negative 3?
Yeah, the 2 points are x equals negative 3 and x
That's
equals
a
1.
maximum.
Yeah, how did you know it's a maximum? From here, yeah.
Wait, so where would I draw that on the graph? Like,
Yeah, so what they just want to know is, they want to know where are any maximums or minimums. So we've already got the x coordinates of the maximums or minimums. We just now need to actually say even more specifically where are they on the graph. Just find their y coordinate as well.
Right,
And your answer's going, for each one's going to be a coordinate.
okay, because I want to know where to draw it on this. So you'll draw it on this? You will do it yet?
Yeah, at the moment we don't even know. It could be up above there. It could, yeah, I would say, yeah, we don't know how high up it is. It's confusing. Hey, yeah, this is the original one.
Wait, how is that the original function?
Because the original is a cubic. This is the derivative.
But wouldn't it be decreasing? Wait, what?
I'll just very quickly go back here. It is confuzzling stuff. And the reason why, here's the derivative. Here's a graph of that derivative that we just found. And notice it's positive to begin with. The derivative is positive to begin with. So meaning it's going up. the original, and then it's negative, the gradient's negative, so then it goes down, and then it's positive again, so then it goes up. It is confuzzling stuff. This whole idea. It's good that you're asking questions because it's good to go over it again and reinforce it. So we don't know how up and down on the y-axis the original function is. We just know that it goes up and then down and then up.
Wait, so shouldn't it be different then? If it's positive first.
Yeah, so going upwards, going increasing.
Going down.
Oh, it just means this graph continues infinitely that way and continues infinitely that way. So it kind of like goes like, you know, it's going up like wonk, that kind of thing. They're really kind of more like roller coasters that go up and down. Lauren. Okay.
Uganda does not have a nice way.
Yeah. So then you Owen. I just have to spread it. I can't always pick on poor Owen.
It's either born. Yeah, it's like.
Well,
I feel like I don't.
why are you even on your laptop? Anti-Asia. Oh, isn't it? Sorry. You totally look like you weren't at all. Okay. I'm just picking on you. Poor Lauren. You picked on. Okay, so here's the original function. So we're pretty much got an almost perfect answer. We know that at x equals -3, it's a maximum. At x equals 1, it's a
Minimum.
minimum, yep, because x equals -3 first and then x equals 1 next. We just need to give a perfect answer. We need to also give its y coordinates. How can we find the y coordinate at x equals -3? What could we sub -3 into?
Into that equation.
Yeah, into the OG.
The OG.
Yep, into
Oh,
the
not
OG.
the derivative, the OG.
Yeah, that's important. Yeah, sub it into the OG. So we just now need the y coordinates. So let's just say we just now need the y coordinates.
I feel like this. It just makes up
We just now need the y coordinates. So it's f of -3. So remember you're subbing it into the original, into the OG. So it's 4 brackets -3 cubed.
Oh.
So see, I've subbed it into the original. And obviously, you know, that gives you 108. So we know we've got a maximum. We know we have a maximum at -3, 108. And we now need to do the same thing for the minimum. So f of 1, it's 4 times 1 cubed plus 12 times 1. Is that plus? Sorry? No, it's -36. Sorry about that. That's a minus there because the original's got a minus. And that gives you, I think, let me know if anything's wrong, -20. So our final answers are, they say find the relative. Use the first derivative to find the relative extrema, any maximums or mins. The first answer was there is none. So we've got a maximum, as you said. So maximum at -3, 108. And we have a minimum at
Look little there.
that's -20, if you can follow that at all. So that's what our final answers would look like. And this would be, there is no max or min. That would be the answer to that one. No max or mins. And this was the reasoning behind it.
Does that say plus 36? Yeah.
Minus 36? Minus 36.
Yeah, it's just the board goes a bit wonky here. It's gotten really bad. We need to get new boards in here, don't we?
Why did it do?
Yeah, I can tell you. I think it's because the original function, yeah, -36x had the original function, yeah. Yeah, exactly, yeah. But that's very good questioning because that's the kind of stuff people would get confused by. So that, by the way, is a -36. Yeah? I'll try to fix that.
Why didn't you do squares?
What was the original? Let's see, what was the original? Oh no! So does that mean my answers are wrong?
Yes.
Probably.
That's what Donald Trump said in the review.
So this one will be the same. You are done. Well picked up on. So the first one will probably be the same because 1 squared is still just 1. But you're right, the -3 one will definitely be different.
How did you get 1 of 8? When 36 times 307 is just 108.
Yeah, it's probably not going to be 108 anymore.
No, but I'm saying
Oh, I might have typed it.
you didn't even do it right the first time.
I might have typed it in the calculator right. Oh, wait. Can you please calculate? Can you please calculate 4 times negative 3 cubed plus 12 brackets negative 3 squared minus 36 brackets negative 3? It might actually still be 108. I might have typed it in the calculator right. I might not have though.
I was going to shut it up, but it's over, so I didn't.
It is 108, yeah.
I didn't
Cool.
get that. Oh, wait, never mind.
So that was lucky. I didn't write it down correctly, but luckily I put it in the calculator with the squared. But I'm glad you picked up on that, or else that would have thrown a lot of people. So our answers would be that there's a maximum at this coordinate and a minimum at that coordinate. Holy moly. And now we're still going to do the third one. Yeah, sure thing. Here you go. So there's our final answer.
You got negative 108, right, Lauren? Negative? No, I got negative. Okay. Negative 36 times 72 plus.
I just have to do that. It's like a problem. There you go. There you go.
I got negative 108 plus 108 plus 108.
Can you follow this at all, Lauren? Like that's a minus there, by the way. That's a minus. Yeah, and that's a 20. Minus 20.
Oh, it is when you come out of your shell.
Did you have lunch?
I did switch, but that's just so me up. No, I really
You just need something to dip in there, like even if it's celery sticks or bread or something.
What did you have? You were like, I had soup. I didn't eat soup one time a year. That's after Christmas when you go to the tractor and hand bracket. What? That's why they make this giant shirts. Your hands bracket. I only have soup one time of year where after you eat the Christmas turkey and ham, you dump the wrap into soup.
Okay.
Okay, so we've still got this. Oh, whoops, sorry.
Mine's like after Christmas too. Each meal is like turkey.
I am done. Just like
Sure thing. There you go. There you go.
I got 12.
And then we've still got this third one to do. Good, yay.
You hate them?
It's like I like roast potatoes.
I hate it's my favorite between ham and
It's
I
not
just love it.
but I like
Cassava pot.
She's like, my Christmas is always crazy. I just like ham, macaroni and cheese, goes all fine.
Okay, we're good. Katie, what is the value of the first derivative of the third function? It's from the previous page.
We have 4 minutes.
Yeah, like negative 14x over that kind of thing.
No one, are you going to do Christmas cards this year?
I'm involving you.
I'm never going to buy.
Yes. Everywhere.
This is the awkward one.
I'm involved.
TJ.
Okay. Interacting.
Oh, they are recording this. You keep saying it's really hard, but I don't see the recording the way in the corner.
Yeah, it's minimized.
Oh gosh, I'm not scared. You keep saying it's really hard.
Yeah, because for some reason, it's right down there. It's the board so out of whack that you can't see the board. Out of whack. Yeah. So remember, we kind of came up with that from a previous one. We kind of came up with the gradient thing. Okay, so remember this is dy dx. So can you remember from this one, from the previous one, To the left of the asymptote, was a gradient positive or negative to the left of the asymptote?
Positive.
It was positive, yep. And to the right of the asymptote? Negative. Close, it was positive.
Negative.
Yeah, negative,
Why
negative.
are you going through this information?
Wait, we're talking about the
Previous page. Previous page, yeah.
Yo, but how do you know that?
Positive. Yeah, I remember. This looks like remember that ass. How and you didn't draw it.
Why did I draw it?
Cool, you don't pay attention. I do pay attention.
That was probably when you were getting your water. So here you go, here's the original one, just reminding you. So what we did was Calvino, because this one's a much harder one.
Yes, Dan, but not that.
So look at that.
Are those numbers for you?
The original. Oh, but actually, to be honest, you'll probably get the same with the derivative too. Do you want me to show you? Yeah. Oh yeah, sorry, yeah, I should have had y. But yeah, because see, like the nature of the derivative, like see the derivative's kind of got that too. Phillies, see the derivative's got that too. So it probably will be the same. But yeah, so here's the original. I'll just focus on the original. This one is a harder one. It's a rational function. So remember, this one had the asymptotes at x equals -4. This just, yep. This is the original one. So just by looking at that one, are there any maximums or minimums on this graph? On the original? Yeah, where's the, what can you see on there? A maximum or min? There is something. There's one thing. There's one thing.
Just zero.
Maximums or min?
Zero.
What we're looking for?
Maximum.
Yeah, whereabouts?
Zero.
Oh, you mean here? Yeah. Okay. At x equals 0. Here's a maximum. Yep. So we have a maximum here. So we might want to say the OG or the original function. The original function.
I have a crush on you ignoring this.
Has a max at x equals 0. So we found it's got a max at x equals 0. What's the only thing missing from my answer? Tiny extra thing.
Value. I mean, why?
The y value, yeah. So we just need the y value now.
Why value?
So we just need the y value now. Y coordinate now. So remember to find the y coordinate, do I sub it into the blue thing?
The original.
The original, good. So to find the y coordinate, we sub it into the original. What is this messy looking original thing? So it's y equals, it was x squared, so 0 squared minus 9 over x squared minus 16. What is 0 squared at? What's 0? Yeah.
-9.
Negative 9 over?
-16.
Good. Which simplifies to? Good.
Not when you're thinking about these numbers.
A negative
Yeah,
divided by a negative is that?
Positive.
Positive, yeah. So we just change it to positive.
That looks like someone would divide it like that. I was ready to figure it out too.
Like, I was like, what's a pulse on? Like, oh, right.
So that's what we'll say. We'll say it's a maximum.
Excuse me.
Max at 0, 9 over 16. That's it.
What's the x value? 0. Sorry.
Yeah. At that little point there, the original function has a maximum. This one, the third one, is a bit of a harder one. Whereas the other ones we could do non-calc easily now.
Oh, what the pay attention.
And do you know what we get to do next? The next question we get to second derivative. So we need to, sorry. Yeah, a lot of people are writing that stuff. So now we need to find the derivative of the derivative. Oh gosh, should we do that next lesson?
Yeah.
This is such a slow going kind of topic, isn't it? It really is hard though. It's hard and it's intense. So it's good that you're stopping and asking questions.
Sometimes I feel a little bit disruptive.
Yeah,
Do you find it hard to teach us?
No, but this is a hard topic. This is probably my least favourite topic in the whole course. It is the least favourite topic, and there's a lot to write. I probably, in hindsight, should have given you like a whole page to write something like this. So you're having to struggle. Yeah, we do. But yeah, this